And now in this lecture we'll find out the area of a circle using two different methods. So in the drawing we have a circle, and we have also here square ABCD. We know that this is line segment AP, that is equal to 1 unit sinus length. This is line segment QC, that is equal to 2 unit sinus length. Again, our mission is to find out the area of this circle. So we'll start with the first method. First of all, we know that ABCD is a square, so all the four angles inside square ABCD, all those four angles are right angles. So actually, this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. In the next step, we define the center of this circle. This point is point O. We define the point of tendency of tangent AB. This is tangent AB with this circle. This point is point S. In the next step, we will join points O and S together by a straight line. OS is of course the radius of this circle, so we will define the radius of this circle as x, therefore OS equals to x is the radius of the circle. So here we can implement all 1. So I think we can all 1. According to all 1, the tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the drawing we have a circle, and this is tangent AB, that is tangent to this circle, and this point M. Point M is the point of tendency of tangent AB with this circle. In addition, we have here the radius OM, that is equals to 1. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, all 1. So we can actually implement all 1 in our drawing. In our drawing, we have the radius OS, that is equal to x. The radius OS is drawn to point S, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to all 1. Likewise, we join points O and Q together by a straight line. OQ is of course the radius of this circle, that is equal to x according to our definition. Again, we can implement here all 1. Why? Because we have the radius OQ, that is equal to x. The radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, all 1. So inside quadrangle SOQB, inside this quadrangle SOQB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the sides of this four freezing angle. In total, they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this four freezing angle must be equal to 90 degrees in its size. So inside quadrilateral SOQB, we have four right angles. And according to rule 5, any quadrilateral that has four right angles must be its rectangle if not a square. So we remember to quadrilateral SOQB is a rectangle because it has four right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle SOQB, side SO must be equal to the opposite side QB. But SO is X, therefore QB must be also equal to X units in its name. Likewise, according to the sum rule, in the same rectangle SOQB, side OQ must be equal to the opposite side SB. But OQ is X, therefore SB must be also equal to X units in its name. So, in total, we found out that quadrilateral SOQB is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Each side of this square SOQB is equal to X units in its name. We know that all the sides of square ABCD, all the sides of any square are equal to each other. So in square ABCD, side AB equals to side BC equals to side CD equals to side DA. And especially side AB equals to side BC. So keep going. So in square ABCD, side AB equals to side BC. AB equals to AS plus SB. AB equals to AS plus SB. And side AB equals to side BC. BC equals to BQ plus QC. So in total, according to equation 1, we should find out that AS plus SB equals to BQ plus QC. AS is the missing side, so we leave it as it is. Plus SB. SB equals to X. And it is equals to BQ plus QC. BQ is X and QC is 3. So in total, we should find out that AS plus X equals to X plus 3. Here, we subtract X from this equation 1. So X will get cancelled, and we left only if AS that is equals to 3 units in its name. So actually, this is 9 segment AS that is equals to 3 units in its name. In the next step, we will do a construction. That is to say, from this point P, we will draw perpendicular on the radius SO. Again, from point P, we will draw perpendicular on the radius SO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. When you find the touching point of the perpendicular from point P and SO, this point SN. By doing this construction, we can deduce the small quadrilateral AP and S. Inside the small quadrilateral AP and S, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 freezing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this four-piece cylinder must be equal to 90 degrees in its size. So inside the small quadrilateral A, P, and S, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to the small quadrilateral A, P, and S as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle AP and S, side AP must be equal to the opposite side NS. But AP is 1, therefore NS must be also equal to 1 unit since it's length. Likewise, according to the sum rule, in the same rectangle AP and S, side AS must be equal to the opposite side NP. But AS is 3, therefore NP must be also equal to 3 units in its length. What is the length of the missing 9/7 NO? From the drawing, it is very easy to see that NO equals to SO minus SN. Again, NO equals to SO minus SN. So, I write it down. NO equals to SO minus SN. So, NO equals to SO. SO is the radius of the circle that is equal to X minus Sn. Sn is 1. So in total, NO equals to X minus 1 units in its length. NO equals to X minus 1 units in its length. This is 9/7 NO. That is equal to X minus 1 units in its length. In the next step, we join points P and O together by a straight line. Line segment PO, this line segment PO is of course the radius of this circle that is equal to X according to our definition. So PO equals to X. So in the next step, I will copy the right green triangle P and O in a new page, and we'll implement the Pythagoras theorem on this right green triangle P and O. Actually, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is abbreviation for Pythagoras theorem. So actually, this is the right green triangle P and O that I got from the original drawing. So according to the Pythagoras theorem, in this right triangle P and O, PO squared, that is the square of the hypotenuse, equals to PN squared plus NO squared. So I write it down. So PO squared, that is the square of the hypotenuse, is equal to PN squared plus NO squared. PO is x, therefore PO square is x square, and it is equal to Pn square. Pn is 3, therefore Pn square is 3 squared, that is 9, plus NO square. NO is x minus 1, therefore NO square is x minus 1 squared. So in total, we found out that x squared equals to 9 plus x minus 1 squared. So x squared equals to 9 plus x minus 1 squared. X minus 1 squared equals to x squared plus 1 squared, that is 1, minus 2 times x times 1, that is minus 2x. So here we have x squared both sides of the equation, so x squared will get cancelled. After we cancel x squared in the side of the equation, we left with nothing, that is to say 0. On the other side of the equation, we have 9 plus 1, that is 10. So in total, in this side of the equation, we have 10 minus 2x. So in total, we should find out that 0 equals to 10 minus 2x. Here we add 2x to this equation, and we get that 2x equals to 10. Here we divide this equation by 2, and finally get that x equals to 10 over 2, that is 5. So therefore the opposite PO is equal to x equals to 5 units, and x is also the radius of this circle, so the radius of this circle, x equals to 5 units in its length. Our mission is to find out the area of this circle. Actually, you know that the area of any circle is equal to pi times the radius of the circle squared. Again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius of our circle squared is x squared. So in total, the area of our circle equals to pi x squared. So it is pi, x is 5, therefore x squared is 5 squared. So the area of our circle equals to pi times 5 squared. 5 squared is 25, so in total, the value of this expression is 25 pi. 25 pi is 78.54 square units. So if we found out that the area that we are looking for, that is the area of this circle, equals to either 25 pi square units, or in terms of numbers, the area of this circle equals to 78.54 square units. So we finish with the first method. In the next step, I will present to you how to find out the area of this circle according to the second method. So first of all, you know that all the angles inside square ABCD are right angles. So those 4 angles are all right angles. So this is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. In the next step, we define the center of this circle. This point is point O. We define the point of tendency of tangent AB with this circle. This point is point S. In the next step, we will focus on this common external point, point B. Point B, it is actually an external point in relation to this circle. Why? Because point B is not located inside this circle, nor on the circle. Therefore, point B is an external point in relation to this circle. So, from this common external point, point B, we have 2 tangents to this circle, tangent BS and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BS equals to BQ. According to rule 2, the left of tangent BS is equal to the left of tangent BQ. So, I'll repeat quickly rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle. This is the common standpoint point P. From this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, to this rule 2, they are equal to each other. That is to say, PA equals to PB. We can actually implement rule 2 in our drawing. As I already mentioned before, we have from this common standpoint point B, we have two tangents to this circle, tangent BS and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BS equals to BQ. So if we define the length of this tangent BS as x, then the length of this tangent BQ must be also equal to x, because they are equal to each other according to rule 2. We know that all the sides of square ABCD are equal to each other. That is to say, side AB equals to side BC. So in square ABCD, side AB equals to side BC. AB equals to AS plus SB. AB equals to AS plus SB, and it is equals to BC. BC equals to BQ plus QC. BC equals to BQ plus QC. AS is the missing side, so we leave it as it is, plus SB. SB is x. And it is equals to BQ. BQ is also x, plus QC. QC is 3. So in total, according to equation 1, we should find out that AS plus x equals to x plus 3. Again, AS plus x equals to x plus 3 according to this equation, equation 1. Here we subtract x from this equation, and we get that according to equation 1, so x will get cancelled, and we left only if AS is equal to 3 units in its length. So we should find out that the length of this line segment AS is 3 units, so I write it down. AS equals to 3 units in its length. In the next step, we will extend this line segment AD by straight line until it touches the circle. And we will define the touching point of the extended line segment AD with this circle. This point is point M. So actually, if we focus on this common standpoint point A, from this common standpoint point A, we have tangent AS, that is tangent to this circle is point S, and from the same common standpoint point A, we have here also, if we extend, we draw a straight line from the common standpoint point A, we get here chord PM. Therefore, we can implement here rule 10. So repeat quickly rule 10. According to rule 10, according to rule 10 is true in any circle. So in any circle, if AB is a chord in the circle, you can say that AB is a chord in this circle, and PT is a tangent. PT is a tangent to the circle at point T. So in this drawing, the following equation is true. That PT square equals to PA times PB. Again, PT square equals to PA times PB. So we can definitely implement rule 10 in our drawing. Why? Because in our drawing, if we focus on this common example point A, from this common example point A, we have here tangent AS that is tangent to this circle at point S. In addition, from the same common example point A, we have here chord PM. So this is to say all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, the following equation will be true, that AS square, again AS square equals to AP times AM. Again AS square equals to AP times AM. So I write it down. So if we focus on point A, according to rule 10, the following equation will be true, that AS square equals to AP times AM. This equation is the implementation of rule 10 in our drawing. AS square equals to AP times AM. AS is 3, therefore AS square is 3 squared, this is 9. And it is equal to AP times AM. AP is 1 times AM. AM in total equals to AP plus PM. Again, AM equals to AP plus PM. So in total, we shall find out that according to rule 10, 9 equals to 1 times AP plus PM. So 9 equals to AP plus PM. You can ignore 1 because when you multiply something by 1, it will not change the value of the expression. So you can ignore 1 in this equation. So in total, 9 equals to AP plus PM. So 9 equals to AP. AP is 1 plus PM. 9 equals to 1 plus PM. Here we subtract 1 from this equation, and finally get that PM, the value of cos PM is 9 minus 1, which is 8. Okay, again, we should find out that the length of this chord PM is equal to 8 units. In the next step, we will do a construction. That is to say, from this point O, that is the center of the circle, we will go perpendicular on chord PM. Again, from point O, we will go perpendicular on chord PM. Luckily, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and PM. This point is point N. in conclusion, what we did until now is from this point O, we do perpendicular on chord PM. ON is perpendicular on chord PM. Therefore, we can implement here rule 11. So, I repeat quickly rule 11. According to rule 11, the perpendicular to a chord drawn from the center of the circle bisects the chord. So in the moment we have a circle, point O is the center of this circle. So from point O, that is the center of the circle, we do perpendicular OM on chord AB. Again, from point O, that is the center of the circle, we do perpendicular OM on chord AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule 11, the perpendicular OM bisects chord AB. Again, perpendicular OM bisects chord AB. That is to say, perpendicular OM divides chord AB into two halves. Each half equals to AB over 2. So the first half is AM, this is equals to AB over 2, and the second half is MB, that is also equals to AB over 2. So AM equals to MB equals to AB over 2, according to this rule, rule 11. So we can actually implement rule 11 in our drawing. Well, in our drawing, we have perpendicular ON, that is one from point O, that is the center of the circle. So we have perpendicular ON on this chord PM. So all the requirements of rule 11 are satisfied. Therefore, we can implement here rule 11. According to rule 11, perpendicular ON bisects chord PM. Again, perpendicular ON bisects chord PM. That is to say, perpendicular ON divides chord PM into two halves. Each half equals to PM over 2. So the first half is PN, that is equal to PM over 2, and the second half is NM, that is also equal to PM over 2. So write it down. So according to rule 11, perpendicular ON bisects chord PM. The first half is PN, and it is equal to the second half, that is PN, that is NM, and both halves equals to PM over 2. So PN equals to NM equals to PM over 2. PN equals to NM, and both halves, each half equals to PM over 2. Okay, PN equals to NM equals to PM over 2. PN equals to NM equals to PM over 2 according to this rule, rule 11. But PM is 8, therefore PM over 2 is 8 over 2, that is 4. So in total we should find out that Pn equals to 4 units in its length. Let's say with Pn equals to 4 units in its length. Pn equals to 4 units in its length. So this is line 7 Pn, this is equals to 4 units in its length, according to rule 11. In the next step, we join points O and S together by straight line. OS is of course the radius of this circle, so I write it down. OS is the radius of this circle. So here we can implement rule 1. Why? Because we have the radius OS that is drawn to point S, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside quadrilateral ANOS, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in size. So inside quadrilateral ANOS, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least rectangle if not a square. So we relate to quadrilateral ANOS as rectangle because it has 4 right angles. So quadrilateral ANOS is rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ANOS, side AN must be equal to the opposite side OS. But AN equals to 4 plus 1, that is 5. Therefore OS must be also equal to 5 units in its length. But OS is the radius of the circle. Therefore the radius of the circle equals to 5 units in its length. So we can find out that the radius of this circle is equal to 5 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle is equal to pi times the radius of the circle squared. Okay, again, the area of any circle is equal to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is 5, therefore the radius squared is 5 squared. So in total, we shall find out the radius of our circle must be equal to pi times 5 squared. 5 squared is 25, and therefore in total this expression equals to 25 pi. So in total, we shall find out that the area of the circle equals to either 25 pi square units, or in terms of numbers, is equals to 78.54 square units. So actually, in both methods, we found out that the area of this circle is equal to either 25 pi square units, or in terms of numbers, the area of this circle equals to 78.54 square units. So in the next step, we summarize the lecture. We start with the first method, of course. So, in this lecture, we found out the area of this circle using 2 different methods. So, we start with the first method. In the drawing, we have a circle, and this is square ABCD. We know that this is line segment AP, that is equals to 1 unit in its length. This is line segment QC, that is equals to 4 units in its length. Again, our mission is to find out the area of this circle. So first of all, we know that all the 4 angles inside square ABCD are right angles. So those 4 angles are all right angles. In the next step, we define the center of this circle. This point is point O. And we also define the point of tendency of this tangent AB with this circle. This point is point S. In the next step, we join points O and S together by a straight line. OS is the radius of the circle. We define the radius of this circle OS as x. So here we can implement rule 1. Why? Because we have the radius OS that is on to point S, that is the point of tendency of tangent AB with this circle. And whenever your radius that is on to the point of tendency, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and Q together by side line. OQ is the radius of the circle that is equal to x according to our definition. Again, we can implement rule 1. Why? Because we have the radius OQ that is equal to x. The radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle. And whenever your radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the sum rule or 1. So inside quadrilateral OSBQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OSBQ, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle, not a square. So we revert to this quadrilateral SOQB, it's a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle SOQB, side SO must be equal to the opposite side QB. But SO is x, therefore QB must be also equal to x units in its length. Likewise, according to the symbol, in the side rectangle SOQB, side SB must be equal to the opposite side OQ. But OQ is x, therefore SB must be also equal to x units in its length. So in total, we shall find out that quadrilateral SOQB is not a rectangle but a square, while because of the fact that all of its sides are equal to each other. Each side of the square equals to x. We know that in square ABCD, side AB equals to side BC. Okay, in square ABCD, all the sides of square ABCD are equal to each other, and especially side AB equals to side BC in square ABCD. AB is AS plus SB, and BC is BQ plus QC. Here AB is AS plus SB, and BC is BQ plus QC. So in total, according to equation 1, AS plus SB equals to BQ plus QC. AS is the missing side, so we leave it as it is, plus SB. SB is x, and it is equals to BQ, that is also x, and QC is 3. So in total, if we found out that SB is x, BQ is also x, and QC is 3. So in total, according to equation 1, AS plus x equals to x plus 3. Here we substituted x for this equation 1, so x will get cancelled, and we left only with AS, that is equals to 3. This is the missing line segment AS, that is equals to 3 units in its length. In the next step, we did the construction, that is to say, from this point P, we draw perpendicular on the radius SO. Again, from point P, we draw perpendicular on the radius SO. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So inside the small quadrilateral AP and S, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral AP and S, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle, not a square. So we relate to the small quadrilateral AP and S as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle AP and S, side AP must be equal to the opposite side NS. But AP is 1, therefore NS must be also equal to 1 unit in its length. Likewise, according to the symbol, in the same rectangle AP and S, side AS must be equal to the opposite side NP. But AS is 3, therefore NP must be also equal to 3 units in its length. What is the length of the missing line segment NO? NO equals to SO minus SN. Again, NO equals to SO minus SN. So NO equals to SO, that is x, minus SN, that is 1. So in total, NO equals to x minus 1 units in its length. In the next step, we join points O and P together by certain OP is of course the radius of this circle, that is equal to x according to our definition. So in the next step, I copied the green right angle P and O in a new page, and we implemented the Pythagoras theorem in this right triangle P and O. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle P and O that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle P and O, P O squared, that is the square of the hypotenuse, equals to Pn squared plus No squared. Again, P O squared equals to Pn squared plus No squared. PO is x, therefore PO squared is x squared, and it is equals to Pn squared. Pn is 3, therefore Pn squared is 3 squared, that is 9, plus On squared. On is x minus 1, therefore On squared is x minus 1 squared. So in total, we found out that x squared equals to 9 plus x minus 1 squared. So x squared equals to 9 plus x minus 1 squared. X minus 1 squared equals to x squared plus 1 squared minus 2 times x times 1, that is minus 2x. So in total, we found out that x squared equals to 9 plus x squared plus 1 minus 2x. So we have x squared on both sides of the equation, so x squared will get cancelled. After we cancel the x squared, in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, minus 2x. So in total we shall find out that 0 equals to 10 minus 2, 0 equals to 10 minus 2x. Here we added 2x to this equation and finally found out that 2x equals to 10. Here we divided this equation by 2 and finally found out that x equals to 10 over 2, that is 5. So the radius of this circle, x equals to 5 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius squared is x squared. So in total, the area of our circle must be equal to pi x squared. The area of our circle must be equal to pi x squared. But x is 5, therefore x squared is 5 squared. So in total, the area of our circle must be equal to pi times 5 squared. 5 squared is 25, so in total the area of this expression is 25 pi. So in total we shall find out that the area of this circle equals to either 25 pi square units, so in terms of numbers the area of this circle equals to 78.54 square units. We finish with the first method. In the next step I presented to you how to find out the area of this circle according to the second method. So first of all, you know that all the angles inside square ABCD are right angles. So those 4 angles are right angles. We define the center of this angle, this point as point O. We define the point of tendency of tangent AB with this angle, this point is point S. In the next step we focus on this common standpoint, point P. From this common standpoint, point B, we have 2 tangents to this angle, tangent BS and tangent BQ. And according to 2, they are equal to each other. That is to say, BS equals to BQ. So if we define the ref of BS as x, then BQ must be also equal to x because they are equal to each other according to rule 2. So BS equals to BQ equals to x. We know that all the sides of square ABCD are equal to each other. That is to say, side AB equals to side BC. So in square ABCD, side AB equals to side BC. AB equals to AS plus SB. Again, AB equals to AS plus SB. And it is equals to BC. BC equals to BQ plus QC. Again, BC equals to BQ plus QC. So in total, according to equation 1, we have found out that AS plus SB equals to BQ plus QC. AS is the missing side, so we leave it as it is, plus SB. SB is x, so we substitute SB by x. And it is equals to BQ, so BQ is also x, plus QC. QC is 3. QC is 3. So in total, according to equation 1, we actually found out that AS plus x equals to x plus 3. So here we substitute x from this equation 1, so x will get cancelled, and we left only with AS that is equals to 3. So the rest of this BC97 AS is 3 units. In the next step, we extended 97 AD by a straight line until it touches the circle. We define the touching point of the extended 97 AD with this circle, this point is point M. So if we focus on this common external point, point A, from this common external point A, we have here tangent AS, the tangent to this circle is point S, and from the same common external point A, we have here chord PM. So all the requirements for rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, AS squared equals to AP times AM. Again, AS squared equals to AP times AM. Okay, again, according to rule 10, if we focus on this common standpoint, point A, the following equation is true. That AS squared equals to AP times AM. AS is 3, therefore AS squared is 3 squared, that is 9. And this equals to AP. AP is 1 times AM. AM in total is AP plus PM. Again, AM in total is AP plus PM. So in total, we shall find out that 9 equals to 1 times AP plus PM. AP is 1. So here you can ignore 1 because anything that is multiplied by 1 will not change the value of the expression. So you can ignore 1 in this equation. And therefore we get that this equation will be equal to 9 equals to AP plus PM. After we ignore 1, 9 equals to AP plus PM. So 9 equals to AP, AP is 1 plus PM. So in total we found out that 9 equals to 1 plus PM. Here we subtracted 1 from this equation, and finally found out that PM equals to 9 minus 1, that is 8. So this is for PM, that is equal to 8 units in itself. In the next step we did the construction, that is to say from this point O, that is the center of the circle, we do perpendicular on chord PM. Again from point O, we go perpendicular on chord PM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord PM. This point is point N. So in conclusion, actually from the center of the circle, that is to say from point O, we go perpendicular on chord PM. So all the requirements of rule 11 are satisfied, and therefore we can implement here rule 11. According to rule 11, perpendicular ON, that is one from the center of the circle, that is to say from point O on chord PM, bisect chord PM. Again, according to rule 11, perpendicular OM, that is one from the center of the circle, bisect chord PM. That is to say, perpendicular ON divides chord PM into two halves. Each half equals to PM over 2. So the first half is PN, and it of course equals to the second half, that is NM. Each half equals to PM over 2. Again, the first half is PN, that is equals to the second half, that is NM, and each half is PM over 2. So PN equals to NM equals to PM over 2. PM is 8, therefore PM over 2 is 8 over 2, that is 4. So in total, from this long equation, we derive that PM equals to 4 units in its length. PM equals to 4. So this is nice image PN, that is equal to 4 units in its length. The next step, we did the construction, that is to say, from this point O, actually, we join points O and S together by straight line. OS is the radius of the circle, because it starts from the center of the circle, that is to say from point O, and then at point S, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore OS is the radius of this circle. Here we can implement rule 1, because we have the radius OS, that is 1 to point S, that is the point of tendency of tangent AB with this circle. Whenever your radius is 1 to the point of tendency, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside quadrilateral NASO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its side. So inside quadrilateral NASO, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this right angle, not a square. So we revert to quadrilateral NOSA as a rectangle because it has 4 right angles. But we also know that opposite sides of a rectangle are equal to each other. So in rectangle AN OS, side AN must be equal to the opposite side OS. But AN in total equals to 1 plus 4, that is 5, therefore OS must be also equal to 5 units in itself. But OS is the radius of the circle, therefore we shall find out that the radius of this circle is equal to 5 units in itself. Radius equals to 5 units in itself. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must equal to pi times the radius of our circle squared. The radius of our circle is 5, therefore the radius squared is 5 squared. So in total, the area of our circle must equal to pi times 5 squared. 5 squared is 25, therefore in total this expression equals to 25 pi. So actually in both methods we found out the area that we are looking for in this question, that is the area of this circle, is equal to either 25 pi square units, so in terms of numbers, the area of this circle in both methods is equal to 78.54 square units. Okay, thank you very much.